Thank you all for coming here. We are Xaoc Devices from Warsaw. My name is Marcin, this is Maciek, and this is Tomek. And we'll play some patches for you today, then explain how you can use our modules in a creative way. We can, of course, also answer all the questions you have about our latest modules, like especially Drezno, Odessa, and Zadar. Okay, so let's get started. was kind of easy patch, but I wanted to show you that you can use our modules. Of course, not only our modules in that patch, but the core of that patch were our modules. For example, the Belgot filter has been used as an oscillator for the bass, and of course the main melodic source for actually two sequencers was just one Odessa oscillator, our new one, which is not available yet, because you have two outputs from it, so you can use them in relation but kind of independently, because the groups of harmonics are distributed the other way, so actually you get different timbres from it. Also, I've been using our utility sequencers called Tirana, which are only 4 steps, but you can use them for ratcheting and step repetitions. You can obtain pretty much complex waveforms and rhythms. And the CV sequence from Tirana has been processed by our Drezno, which we'll elaborate more later about. Actually, this DAC and ADC converter, so you can use CV sequence to generate trigger patterns and to automate other things in the system. For example, it has been used for the kick and for the kind of other percussive sound, which has been processed by flipping the bits of the audio signal. Of course, the last step in that patch was our voltage controlled mixer, which has been used with actually 2 auxiliary effects, like delay and reverb. Also, the whole percussion has been distorted and processed by our Kamieniec, which is a phaser, but you can use it also as a really kind of an generator and saturator and a distortion module and whatnot, actually. And all the envelopes has been provided by our new Zadar module, which is a quadruple digital envelope generator, which provides really complex shapes that you can animate and deform. So I've been using them with our VCA and for a bit modifying the pitch of the bass and to generate transients for the bass. So that's pretty much all. And now Maciek will take more about theory behind our modules, the purposes of use. So, okay.
Hi.
Hi.
First of all, I will talk about our Drezno module, which is a little bit older unit produced last year, but not everybody understood how it works. It was a little bit mysterious for some people, and I would like to explain the basics and show some application examples. So, let me switch the screen to show you some slides. So, Drezno. Louder. Okay.
Louder.
Drezno consists of 2 parts: analog to digital converter and digital to analog converter. So you have an analog input and 8 binary outputs on the left side, and the clock input here, and also some 8 digital gate inputs, which are binary numbers, and they are converted back to analog domain, and there's an analog output at the DAC side of this module. Drezno speaks digital language, digital numbers, which are represented by a sequence of zeros and ones. This representation, we believe, was invented by Leibniz, hence the name of the subsystem we propose, which Drezno is the head of. So with binary numbers, we represent values by changing zeros and ones on different positions. This is the lowest significant position, and this is the highest significant position. As you can see, when we move from one value like 0 to 1, there is just a single switch of one single bit. And to get from 1 to 2, this bit gets flipped back to 0, and another bit switches to 1, and so on. So growing values will give you more and more ones and at higher positions. Okay, and you can see that the highest value that you can represent with 8 bits is 255, and in the middle of this range there is a very interesting switch from all ones to just 1 at the highest position and zeros. So if you look at them from top to bottom, the least significant bit flips in the most rapid way, and the most significant bit flips slowest. So an analog to digital converter that uses such a representation makes translation from continuous analog voltage to a sequence of binary numbers. So every voltage that falls within some range interval, which we call quantization interval, is represented by the same sequence of numbers. So there's some inaccuracy in this representation, and with 8 bits we have 0.5% of inaccuracy actually. And you can see that these voltages are mapped to numbers, and we can do the same in the opposite direction by mapping these values, these numbers, back to some voltage, and this voltage will be in the middle of this interval. We call it quantization distortion or quantization error, the difference between the original value and the value that will be recovered from the binary representation. Okay. So what's the meaning of individual bits on the outputs on the left side of Drezno? If you look at the highest, the most significant bit, it tells you if we are just at the upper or lower half of the dynamic range of the signal. So whenever your waveform is in the upper half, we have 1 at the output of the most significant bit and 0 if not. So what happens if we remove just this single bit from this representation? It will just remove the information that we were in the upper half of the range, and the whole waveform will flip to the lower side. Okay, so this is what can be done with Drezno if you just drop this single bit and replace it with 0. What happens if you invert this single bit? You just replace the upper and lower portion of the waveform, half of the waveform, in this way. So you have some kind of digital distortion imposed on your waveform by inverting just the single bit. I will show you this in a moment. What happens if we consider the next bit, the second, which is B6 actually? We split each half of the dynamic range into half again. So it tells us if we are in the higher or lower quarter of each half. So this bit will tell you if this waveform is in the range shown in pink or green accordingly. Again, if we invert this bit, these parts will flip. Okay? And this happens for every bit. If you go down, every part is split by half, and so on and so on. So you can introduce some distortion, and you can generate some pattern from crossing the borders between quarters, halves, 1/8, and so on. Okay? Very important thing about application of analog to digital and digital to analog conversion is adapting the range of the signal to the resolution of the converter. That's why we have two sliders on each side of Drezno to adapt the signal to the dynamic range that the converter chip can handle, which is 0 to 5 volts. So we can attenuate and offset your waveform so that it will not be clipped or distorted at the ADC, and also it allows you to bring it back to the original dynamic range or polarity or whatever you want. Of course, you can set them whatever you want, however you want, but in order to get exactly the same looking waveform, you need to set these very carefully. Okay, a very important aspect of quantization is sensitivity to noise. If you consider being just at the edge of two quantization steps, a presence, if you have a value that falls into this or this range, any little amount of noise will cause the resulting digital representation to be switched from this word to this word. And you can see that several bits flip actually, not only the lowest significant bit, but also higher bits. And if you recall that at the middle of the range there is all ones and 0 at the highest position, and the next step is 1 and zeros, also the most significant bit can flip due to the presence of noise. So it is actually very important to use a clock to stabilize the output of the converter if you want to have stable gate signals at these binary outputs, if you want to use them for rhythmic purposes, for clocking devices and so on, the sequencing. Okay, so now let's talk about some applications of Drezno. One of the perhaps obvious application is that you can generate patterns of binary signals from any analog signal. So you can put some LFO or envelope or a sequence to the input of the ADC part of Drezno and use some clock. That's very important to get clocked or synchronized changes, and you will observe that the most significant bit will produce very slow patterns, and if you go down, the patterns will be more quick and complex depending on the waveform, the actual waveform which is used here. You can use the DAC, the digital to analog converter, the right side of Drezno, for generating sequences from gates. For example, you can use some outputs from frequency divider or from various sources. You can synchronize them, and depending on what changes, what values are mapped here, you will have some analog pattern which is produced. So it's like sequencing without a sequencer. It's an alternative way to produce some melodies or something like that. The important thing is that if you drop some lowest significant bits, you have actually a number of active lines. So the number of combinations which are used at the input equal the number of different voltages which are produced, which is 2 to the power of n, and n is the number of active lines that you use. So with 5 lines, we will have 32 distinct voltages produced here. So if you have a repeating sequence here, you will have a repeating pattern of voltages at the output. Of course, you can use this as a quantizer. If you drop some lower significant bits and you introduce some smooth waveform at the input, you will have a quantized waveform at the output, but also we can use it for quantizing pitch voltages, for example. But the important thing will be to set very accurately the width of the quantization step, which is the gain of the DAC part of Drezno. You can employ Drezno to perform some very complex wave shaping, and you can twist your waveform by switching bits, inverting some bits. You can remap low bits to high bits and so on, and you get from a sinusoid you can get something like that. I will show you some examples on the scope in a minute. So that allows you to generate fractal like waveforms, which are very nice for modulation, especially for pitch modulation. And finally, you can introduce an analog feedback between the output of the DAC to the output of ADC and produce a chaotic device that is capable of generating very interesting sequences of voltages which can be modified or altered by changing the mapping between those bits. If you look carefully, each of those lines represent the combination of those lines represent a number of states. The number of states is again 2 to the power of n. So this chaotic or pseudo-chaotic device will produce sequences which are seemingly chaotic, but actually they will be repeating, and the repeating is due to the limited number of combinations that can be produced. Again, 2 to the power of n. Okay, so finally we have some expanders to Drezno. One is available now, others are coming. This one, Lipsk, facilitates just inverting individual bits. It can be done manually by using those tact switches or automatically through gate signals which can be introduced to those jacks. You connect Lipsk to Drezno by connecting the ribbon cables at the back of the units from output of Drezno to input of Lipsk and vice versa to get a loop, and when you press this link button it will feed the bits from ADC through Lipsk to normalized connections of the jacks on the right side to DAC. So you can always replace any bit by putting a cable into it, but if you don't, it will be a bit from this side run through Lipsk and back to Drezno. Future expanders will introduce some more interesting mangling of bits in value and time domain. So expect some more complicated solutions here. Okay, now I'd like to show you what happens to a waveform which is fed, a waveform from battery, a sinusoid which is fed through Drezno, and I've engaged the link button here which automatically maps the bits from ADC to DAC, and you can see the yellow trace showing the original analog waveform and the blue trace showing the output of Drezno. As you can see, they are not identical because it is sometimes quite hard to get exactly the gain and offset, but they can be matched visually very closely. And what happens if we, for example, as I said, replace one of the bits with 0? For example, the most significant bit, as you can see, that's the flipping of the lowest part of the, oh, I'm sorry, the noise, okay. This is replacing the bit number 6, 5, and so on. Now, I'd like to route one of the bits through an inverter, which will be an inverter from the IntelliGel Spock module. So I am replacing the most significant bit, and you can see that pattern that I've already drawn on the slides. I'm doing it with lower bit and another one, and so on. But as I said, you are not limited to inverting just one bit. You can do it in more bits, and you can exchange them. You can cross patch from this bit to this one. Let's say from this bit to this one, and so on. So we have very interesting way to twist your waveforms in a digital meaning, very different from analog wave shapers and wave folders and so on. Now I will use Lipsk to switch the bits. Yep.
Can you just automate this?
Of course, yes.
It's because it is always you are working on just gate signals. This whole 8 bits are 8 gate signals, and you can do all logic processing as with usual gate sequences on the bits, and just translate later from this bit gate signal to analog signal, which is just fluent control voltage, and it will give some representation of these changes made in this digital domain when you just process the gate signal really. So it is really something different than process just analog signal, and give you really lots of possibilities, and always you need to do, maybe don't need, but you can do with 8 different signals some processing, but it's still just the gate, so just switching on and off some of this gate signal will give you very interesting effects. So it's really a cheap kind of processing, because you don't need to use some complex modules for this.
Okay. I've patched an output from Batumi to one of the jacks in Lipsk to show you what happens if you automate this flipping of bits. One of the one of the buttons is blinking here because I've patched a gate from Batumi to this input, and it just flips the single. The single part. Okay.
What does it mean for the sound? Your input is sine signal?
Yes, the input is a sine. Pardon?
How does the sound change? No longer a sine signal or something?
Yes,
Now
I
it's
should.
a lot of overtones and
Yeah, it depends on if you use that for audio signals or modulation signals. I would say that for CV, that is used for pitch, you can generate some arabesque patterns, which are very interesting here. And in audio signal, yeah, you introduce some harmonic distortion, very harsh distortion. Yes, some people treat Drezno as a elaborate bit crusher, but that's not the main purpose of this module. Yes, it can work as bit crusher. Actually, those converters work in very high rate. There's an internal clock of nearly 2 megahertz, so there's no aliasing involved here, no audible aliasing, I would say. You hear all those distortions only due to quantization or remapping the levels. That's it. but of course you can introduce your own clock and you will have the effects of sampling involved into the sound as well. Any more questions?
Okay, so maybe I will show now the patch I have prepared. There are all of our modules that we are talking about today used here, but the main source of the all sequences I use in this patch I will present are just from the Drezno. So as you can see, the signal input, audio or control voltage in this case, will be fed with the waveform from our envelope Zadar, and everything will be the triggering of the envelope will be synced with the clock, which will run the analog to digital converters. It will just, if I will change the speed of the clock or division of the clock, I will get some more complex sequence of these gates. Here you can see on the LED the activity of these gate outputs. They are really okay. They are really quick if you use the internal clock, but because it's 2 megahertz, but you can really slow down it to just a regular clock rate, and it will act a bit like a sample and hold, but it will hold the voltage on the output, but also it will let you have a slower sequence of these gates that are representation of the beats, and you can use it just to trigger your drums, samples, envelopes, or whatever. What's really what I like really in the Drezno is that it's a bit chaotic. It will give you repetitive sequences, but sometimes just the value will change a bit because of the amplified noise,
Yeah.
and it will give you completely different at this one moment representation on the output of the beats. So it's a bit like some really
Random variation.
yes,
of the pattern.
it's random variation, but it gives you this human feeling to this pattern. It's complex, but also still you have some grooves. So I really like this. Okay, there is a bit of a mess here, but here is the Drezno and Lipsk, which are the heart of this patch really. Just only sound source which I using is the Odessa, our new additive oscillator, and for the drums just Belgrade, which I'm pinging with the envelopes from Zadar. So okay, so I hope you will like this. I said, all the sounds was really taken from our forthcoming oscillator Odessa, and all the sequences was generated by Drezno. If you can hear, this is the waveform that is fed to the Drezno, and the sequence is based on just this repeating waveforms. And during this set, I here changed the clock from the one to another. The one is just divided by 2, and another is multiplied by 2, and another is multiplied by 4. So I'm not sure if you noticed this moment, but when I changed this, everything was a bit speed up, and the sequence changed. But it just was like the same sequence, but with like bigger resolution, for example. So it there was some more events that was happening during this sequence. And here are just these bit outputs. It's a bit of a mess, but they are just triggering the other sequences, running the drums, and just the envelopes for 2 voices taken from Odessa. As Marcin said, we have on Odessa 2 individual output of different harmonics from the oscillator, so you can use this as a 2 audio source.
Actually, it has 3 outputs.
Yes,
there is an additional output for the fundamental.
Yes, there is also the output for the fundamental. So this is this basic sine wave, which will give you the pitch of the tone. Later, I was using also the second half of this Drezno, which was generating the sequence that was running the oscillator. So this was this melodic sequence. I was using a bit slower clock to set the quantization of this sequence to have the slower sequence, melodic sequence, than the faster rhythm. So we can use 2 different clocks really with both halves of the Drezno to obtain faster or slower changes on the output. So this was really, I used these things just to chromatic quantize the sequence, but the sequence was generated based on this waveform. It was like really sample and hold this plus this some more chaotic behaviors that are when you translate analog signal to digital and digital to analog, everything what was Maciek talking about. I had also another Drezno, and this one was used as a bit crusher. So okay, so this is just the sound of the Odessa bit crushed by the Drezno, and here you see these flipping beats. And they will give you just these different flavors of the distortion, because each flipping beat will distort the signal in different way, as Maciek was showing on the slides. So if I take this gate signal out, I can just flip it completely if I will change all the beats, because it will just flip in the face. But if I will leave any beat unflip it, you can hear the subtle effect when I flip only the less significant beats, because it will give you just small distortion, but with flipping most significant beat, it is really hard. so maybe now I will also explain a bit what I was doing with the Odessa. These two knobs just sets the different groups of harmonics to output. So okay, so maybe I will leave with Maciek, which will show you exactly in what is happening with the Odessa, and just provide some sounds if you need it, because he really will do this a bit better.
Odessa is an additive oscillator. Okay. Without cheating, I mean the procedure for producing the sound is basically to generate every harmonic partial, every sinusoid that the sound consists of separately. So it's a digital oscillator that produces up to 2,500 of sinusoids in real time, and all of them have several parameters that can be modulated in real time. And these parameters, there's plenty of parameters, of course, with this number of sinusoids. So we decided to develop some set of macro parameters that allow you to shape the sound in most flexible way with these limited number of controls. So first of all, of course, we have a pitch, and you can determine how many sinusoids are there. I will show you on a spectrum analyzer what happens if I change this. Okay, so this is the fundamental sinusoid, and adding more of them will produce a sound, and you can see that the overall level of them is decreasing because we have a volume compensation that allows you to keep the loudness of the whole mixture on, let's say, equal level regardless of the number of the richness of the spectrum. Okay, so this can go very high up to some audible limit, and the most important thing here is that we do not generate sinusoids which are inaudible, which are outside the audible range, and thus we avoid aliasing. Okay, this is very important. Other generators are incapable of escaping this limit. There's some aliasing in many digital oscillators, not here. Of course, the number of partials here depend on pitch. So if we have lower pitch sound, it will be very rich, and there will be less sinusoids if I increase the pitch. So we have a control of the number of sinusoids, and we have a control over the shape of the spectrum in several ways. First of all, we can determine the tilt of the spectrum. So we dampen the higher harmonics. It works a little bit like a low-pass filter, but there is no specific frequency above which the filtering occurs. It's just decreasing the magnitude of each harmonic repeatedly. Okay. Now let me lower the pitch to show you that we can also impose a pattern of comb filtering on this set of harmonics, and you have two controls for that, which is called density that tells how many notches of the comb there are in the spectrum, which can be very dense, up to a notch of every second harmonic is filtered out. It's not a filter, it's just manipulating of the magnitudes of overtones, okay? And for this comb we can also determine the uniformity of the notches, so they can be uniform or more dense in the lower part of the spectrum. All those parameters can be animated by external CV. On top of that, we have a control over we have a control on the harmonicity of the sound, which we call tension. So we can have a uniform pattern of equally distant frequencies, or we can stretch the spectrum so that it will become inharmonic. This is something that is unobtainable from any wavetable based synthesis, because this no longer is a periodic waveform. Only periodic waveforms consist of uniform pattern of equally distant harmonics, overtones. And for a non-harmonic sound, which can be very inharmonic, and you can see these harmonics are very different, and also we can make them okay, maybe I will show this lower pitch. They are more and more close to each other, up to a point where when they are so close that the spectrum falls on itself. Instead of growing frequencies, we have decreasing frequencies of overtones, like here. And what you hear is some kind of a pitched noise. Okay, and you can determine the number of harmonics and all the other parameters. The next thing is we may have more than just one pattern of overtones. We can have actually 3 slightly detuned voices, and you can see that every harmonic is replaced by slightly beating set of harmonics, and 5 detuned voices. And of course they can be very much detuned, so you have a inharmonic cluster. But with this and some comb filtering imposed on it, you get very unique sound, I believe, which is perhaps impossible to get from any other synthesis technique. Okay, there's one more parameter that I forgot to tell you about in this comb response. Okay, which is peaking, that determines the selectivity of the comb filtering response from very narrow breaks in the spectrum to very narrow peaks in the spectrum. Like that, it can be very selective. the parameter. So introduce some modulation to that. Also, on top of that, the pattern of overtones can be split to two banks of overtones, and we can say what is the length of the bank. For example, if the length is just 1, every second or each even and odd harmonic will go to left and right output of Odessa, and you can say I wanted, okay, let me go back to flat spectrum. Okay, now we can see that I have a pattern of, this is no banks. I can say that I want odd or even lengths of banks, and in one of the groups of the banks the frequencies can be multiplied or divided by a number. Okay, so you can use these two outputs as two different sounds, or you can create stereo effects with that. So if we combine this with slide the tuning, and so I'm picking. Of course, the length and the division of multiplication factor, the harmonic factor, we call it harmonic factor, can be changed on the voltage control as well. We have a linear input for linear frequency modulation through zero frequency modulation, and since modulating very complex waveforms with through zero deep modulation produces very harsh sounds, it's best to use the fundamental separate output, which is just a sinusoid. This also will be modulated by this linear FM input. So that's it.
Yeah.